Welcome everyone again. Last lecture was pretty intense, as heard from feedback, and the energy was so high. Everybody was engaged. I love it. It's one of my favorite lectures. There's more to come like it. I did go a little bit fast at one point when I was typing in the arrays because I was hoping to finish the crescendo and get to solve the heat transfer problem. Unfortunately, we did not. And so that's why I went a little fast at the end. So we'll pick it up from there. I'll go a little slower. Today we'll repeat where we left off, the last few bits. And if you recall, we were trying to solve this heat transfer problem in a rod. We took the continuous differential equation. We discretized it, converted into a system of algebraic equations, and we put them in a matrix form that looks like this. The coefficient matrix has a neat structure. It's tridiagonal. The main diagonal is mostly consistent of the number -2. The first upper diagonal is all ones except the first entry. The first lower diagonal is all ones except the last entry. And we talked about a mechanism to build an arbitrary sized system of equations based on this discretization, this approach. Because the more points you add, you're just going to make that matrix grow and grow and grow and grow, and it will repeat itself. So we can have machinery that builds an arbitrarily sized matrix. And the idea was, if we know what the entries in these primary diagonals are, how about we build them as one-dimensional arrays, just vectors, and then somehow put them in a matrix, tell Python, put these in a matrix on a given diagonal. And we learned a few tricks to do that. The first step was using the numpy.ones routine that returns an array of ones of size n. Okay, so that helps us build the first upper and the first lower diagonals. And then we just adjust the values at the end, or the first point 0 or the end point 0, as I show here in these two lines of code here. Now, to do the main diagonal, which consists mostly of -2, we just do the same thing, numpy.ones, and multiply it by -2, and then fix the endpoints, which are 1 and 1. So the first entry in that main diagonal is 1. The last entry is also 1. But also pay attention about the size of these diagonals. The main diagonal has size n, which is the number of points on that rod or the number of equations we're solving. The first upper and the first lower are of size n minus 1. So that when you combine them together to make a matrix, everything is going to be consistent. And the next step was to convert these one-dimensional arrays into an actual matrix using the function called diag. So the function diag takes a vector or a one-dimensional flat array and puts it on a diagonal k. The main diagonal is at k equals 0. It's the central diagonal. It's the reference diagonal. You go upper, 1, 2, 3, and so on. Lower, -1, -2, -3. Okay? So we did all that, and we built the full matrix together using this formulation. We built this this sparse matrix, but we stored all the zeros in it because we're not going to worry now about doing sparse storage, etc. That's a topic for a different course. But for now, this gets you all the way through to be able to solve this problem. And then we left off over here, unfortunately. We're going to take this heat transfer problem and actually just solve it, all right? And think about the physics. Again, numerical methods is a set of tools that enable you to solve real problems. Chemical engineering, in electrical engineering, in data science, in statistics, in medicine, and whatever, right? And most of those problems can be narrowed down to systems linear equations, nonlinear equations, regression, interpolation, integration. So you're learning these tools, but also you need to be held accountable to the physics. And I'll discuss this once we start solving the problem. So the fact that you're able to solve a system or you get some numbers and you make a beautiful plot doesn't mean that your answer is correct. You still need to do a sanity check. You still need to verify that your solution makes sense, at least in certain limits. And I'll discuss this as we work through the problem. So grab your Jupyter notebooks. Last time I had this one, what was it called? Fun with NumPy arrays. Okay, so we'll rebuild it. Let's rebuild it together from the beginning. So I'll just go ahead and open a new notebook. And you probably would like to pick up from where you left off. That's okay. If I was going too fast for you last time, we can pick up from here. So I'll just copy the boilerplate. Hopefully that's in one of your older notebooks, other notebooks. Okay, so import numpy as mp and matplotlib.pyplot as plt, and then the magic so that we get scalable vector graphics to produce beautiful plots. Okay, so put this in all your notebooks. That's my advice. All right. So the next order of business is to actually define. I'm going to move this window to crest on here. Let's see. Okay. So I want to solve this problem with this source term. S of x equals some alpha e to the minus x minus a over sigma squared. And we plotted this last time. We'll redo it again. So first, I'd like to define the properties for the problem. And I'm going to make those up as we go. So I'll start with a rod length of 1.0. So meters, that's rod length. Okay, that's the heated rod. Okay. And let's start with 100 points. Number of points or n minus 1 intervals, right? And I will need delta x as well, because delta x, if you recall the system of equations we're solving, on the right-hand side, I have a delta x squared multiplying the source term over k, right? So I need a delta x to be defined. So you can define it a couple of ways. The one I like is just simply taking L over n minus 1. So that's, you have a length L divided by n minus 1 intervals that give equal spaced intervals. So that gives you the length of the interval, right? So constant spacing between grid points. Okay. And finally, we'll create a linear space for the coordinates on that rod, for the abscissa on the rod. We need that because of the source term. The source term depends on x. And also, it will be useful when you plot temperature versus location on the rod. So it's neat to have an actual abscissa on the rod. So it's always useful to do that. So we'll do a linspace, x equal numpy.linspace from 0 to L and n points. All right. So by default, linspace will generate an array of x values starting from 0, ending at that endpoint with endpoints. Okay. All right. So that's behind us now. We will define the source term. So let's create a Python routine for the source term. And the way I think about routines, talked about this last time, I'll keep talking about every time I write a Python routine. Think of a routine as a box that takes some input, one or multiple inputs, and produces one or more outputs. All right? As you design that routine, you ask yourself, from a user's perspective, suppose the user doesn't have access to what's inside your routine. What kind of cool features do you want to give them? What kind of knobs do you want to allow them to turn? Like for this source term, should we allow the user to modify alpha and the standard deviation and the location and so on and so forth? Maybe. It's up to you, right? So you have a lot of flexibility in that. But I know for sure that this source term routine has to return an array including that contains s of xi, right? So that's for certain. The output sometimes is dictated And there are certain things for the input that are required. For example, the location of the abscissa points, right? So at the minimum, I'm going to pass X, and I will hard code alpha and sigma and the other properties. Right, so if you look at what I have here for the source term, it's a Gaussian alpha e to the minus x minus a over sigma squared. Sigma is the spread of that signal. Alpha is a pre-exponential factor. It scales it vertically, like how strong is that value of S. Now remember, this S source term is a heat generation term. So how strong is that fire? Or how strong is that heat being generated inside the wall or inside that material, inside the rod, okay? And A over here is the location of where that peak heating occurs. You could have a double Gaussian or a triple Gaussian or like 10-modal Gaussian. It's up to you, right? You could have a hyperbolic tangent, some weird function. It doesn't matter. It will just work with this system, okay? Now, whether it's going to be physical or not, that's a different question. All right, so let's do alpha equal 1e to the 6 and sigma. So the way I get these Greek symbols, I type the symbol with a backslash as if I'm writing in LaTeX. So I type sigma, and then if you press tab, it will autocomplete into sigma. If it doesn't do that, don't sweat about it. Just type sigma S-I-G-M-A, right? And 0.1 meter, and x0, which is A, or let me call it A, which is the location of the peak. Let's put it at L over 3. Okay, so it will be located 1/3 from X, 1/3 on the left, right? And return alpha times NP dot exponential. And I have a minus, and then X minus A squared over sigma squared. Agreed? Okay. And if you're in doubt, plot it. Okay. So let's go ahead and plot this. PLT.plot. I want to plot the source term as a function of the location on the rod to verify that what I put in makes sense. So source X, right? So X is already an array that contains the spacing. And again, if you're in doubt, print it out. Here's print X. Here are the values, the X values, going from 0 all the way to 1. All of them are equally spaced, okay? So, all right, so let's see if this makes sense. Okay, great. So I'll add a grid, plt.grid. See, the peak is located just about 1/3 at 0.33, right? And sigma is the breadth of that function. And alpha, see that 10 to the 6? It's right there at the peak, okay? And you can verify that. You can do a wider sigma or a smaller sigma, and you'll verify that it gets narrower and narrower, okay? All right. Good? We good? Okay. All right, let's get to the actual array building. All right, so T, the left temperature on the rod, let's just put it at 300. We'll change the numbers as we experiment with this. Let's put it at 300, so that's temperature in Kelvin at x equals 0, at x equals 0, and then T right is 500. So the right end of the material is held at a higher temperature than the left end. So we know that the heat is going to go maybe up from the left, maybe go to a peak and then come down to 500, something like that. Okay, that's what we're hoping. And K, I'm going to consider copper for the heat conductivity. Remember, for heat conductivity, it's the ability of a material to transmit heat. The higher value of the K, the faster the heat is going to equalize across. The smaller the value of the K, the harder it is going to be for the heat to equalize. So what we will experiment with once we get this moving we'll put a very small value of k and a very large value of k and see what the difference is going to be. Okay? So for copper, k is 398 dimensions. All right. Now for the lower diagonal, oh, we didn't specify the number of points, did we? We did. Yeah, n equal 100 points. Perfect. So lower diagonal is mp.1s of size n minus 1. And for the lower diagonal, the last entry was 0, right? Let's see. The lower diagonal, the last entry was 0. So LD minus 1, that gives us the last entry, equals 0. So we're going to set that to 0. Upper diagonal is the same, also mp.1's n minus 1. However, the first entry is 0. Okay. You can put 0.0. Give me a hard time. Okay. Now the main diagonal, MD, is minus 2 times mp.1's of size n, right? And then the first and last entries of the main diagonal are both 1. So the first entry is MD at 0 equal 1. And the last entry is MD at minus 1 equal to 1. Okay. Finally, we can build the coefficient matrix. So these are just the diagonals. They're 1D arrays. If you were to print them out, they will just look. So if you print, they'll just look as flat arrays, right? Print LD is just an array, one-dimensional array of ones, okay, and a 0 at the last point. Upper diagonal, oops, same thing, and the main diagonal has minus 2's everywhere except 1 and 1 at the first and end points. To create the full matrix, which I will call A, very creative name, we'll do mp.diag, which I already imported. Did I import it? I did not import it. Okay, so numpy.diagonal, numpy.diag. We will put the lower diagonal at the minus 1 location, right? So that's the first lower diagonal measured from the main diagonal, which by definition is at k equals 0. So you go to the lower diagonals, you go minus 1, minus 2, minus 3, and so on, right? And then, so np.diag, so this term here, np.diag of the lower diagonal minus 1 will create a matrix of size n by n that's full of zeros except for that first lower diagonal. If you're not convinced of that, let me convince you. We'll just print it out, right? Okay. Let me change the number of points just for visualization purposes. Okay, I'll go 10 points. Okay. All right. So if you do mp.diag, lower diagonal minus 1, see it creates a matrix all full of zeros except for the first lower diagonal. Now I want to add that to the main diagonal, which is again mp.diag md at 0, and then add to it the first upper, mp.diag, upper diagonal at 1. And now that gives us, if we print A, it gives us the system of equations that we're looking for. We rushed through this last time, okay? Today, I hope that you're able to catch up. What's really cool about this is now you can just scale this to any number of points. You could put 1,000 points or 500 points, whatever you like, it will just work, okay? There's not even enough room for this to print it out here. Okay, that's great. So now we're like half the way through. We still need to build the right-hand side. If you think about numpy.linalgebra.solve, takes a coefficient matrix and a right-hand side, and then spits out a solution. That solution, you just call it temperature, right? But you need a coefficient matrix and a right-hand side. So we still need to build that right-hand side. Luckily, that right-hand side is just a 1D array, 1D flat array, so vector, column vector, row vector. NumPy will figure that out. All right, so let's build it. So the right-hand side, b, is equal to minus dx squared, right? So it's minus delta x squared times s over k, right? So times source at x over k. But we also need to fix the endpoints, TL and T right. So B at 0 is TL, and B at -1 is T right. Now this will return an array of the correct size, of size n, a vector of size n. Why? dx and dx are scalars. They're just single-valued scalars. K is single-valued scalar. But source of x, because x is an NumPy array of size n, source of x is also an NumPy array of size n, because that's how we designed source x. So therefore, all that entire statement over there is also an NumPy array of size n. Okay? And again, if you want to confirm that for yourself, just change the number of points so that it's readable. And then there you go. You got a bunch of values, whatever they mean. There's just a bunch of values that are important for this problem. Okay. We are ready to solve. Should we? Do we dare to solve it? Let's do it. Okay. I'm going to put it in here. Finally, solve the system of equations. Okay. Temperature, T, is equal to solve AB. It says, oh, it gave me an error. np.lin algebra.solve AB. There you go. All right. What do we do next? Let's plot it, right? Let's see what the heck we got. Okay. plt.plot. We're going to plot the temperature versus the location on the rod. So on the x-axis, I'm going to put the abscissa. And on the y-axis, I'm going to put T. Oh, look at that. OK. So now that's a temperature profile. What you're looking at is the value of the temperature as you move along the rod from the left end of the rod all the way to the right end. OK. Let's embellish this plot a little bit so we can reason about it. I'm going to add a grid. I really like grid to kind of understand what's going on. All right, so it gives me these vertical lines. Now, does my solution make sense? Does this solution make sense? Like what? Why?
Because it's like hotter on the right side and colder on the left side.
Okay, and is that, you expected that? Why?
Because of the temperature.
Boundary conditions. Yeah, we had 300 on the left and 500 on the right. Okay, what's another more specific test to build on that? What is the temperature on the left? 300, exactly as we expected. What is the temperature on the right? So that tells me that we at least got the boundary conditions right. So let's experiment with that. Let's go ahead and change the right temperature, put it at 400. Oh, look at that. It brought it down to 400. Okay? So we at least have the boundary conditions checked out. Okay? Now, we have a peak. Our peak is at 1/3, right? And over here, it's kind of like around 1/3, 0.4 because of heat dissipation, etc. It's spreading the heat a little bit. So at least we got it right. It's not like we got the peak on the other side of the rod, right? So let's play with that. Let's go ahead and change the peak location to the right side of the rod. 2.0 times L. So that's on the other side of the rod. Okay? Now, look at that. The peak changed to the right-hand side of the rod. Okay? So these are little sanity checks in the absence of an exact solution or an analytical solution, which we assume we don't have now. This is the best you could do, at least as a first-order approach to get a sanity check on your calculation. Okay? Now, I know this is valid. I've verified this with an analytical solution, actually, for this problem. But if I didn't have that, that's the first thing I would look at. Boundary conditions, think about the peak. Okay? But now you have a tool to reason about the physics of the problem. So what would happen, do you think, as we change K, that value, that heat transfer coefficient. As K becomes higher and higher, larger value of K, heat is going to spread very quickly across that entire problem. So what should we expect if the K value is large? A what? A broader peak. So it would go up from 300 and flatten out, right? And then come back to what? To 400? Okay, let's try that. Let's do 1,000 for K. Okay, so you're kind of right, but something is happening, though. So let's continue increasing the value of K. Let's go to 5,000. Oh, the peak is disappearing. Why is the peak disappearing?
Because now one of the sides is hotter in our calculation than it should be based on how the heat transfer.
How about what's happening to the heat? What happens to that heat equation if there's no heating source? So if you take that d2t by dx squared equation, okay, so I'm going to come back to this equation. What if there was no source term? Or what if the right-hand side was 0? What is the heat going to what is the temperature profile going to look like? Straight line, right? Second derivative equals 0 means the solution is a straight line. So we expect, in the absence of any heating, to just have a straight line, straight slope from one end to the other. Now, as you increase K, mathematically what's happening, this term is going to 0. As K approaches infinity, S over K goes to 0, right? Physically, all the heat that is being contributed by the flame is just spreading out very quickly. It's just going out the sideways. Even higher, lower, is just going out through the ends of the rod, okay? It's just going out through the two boundaries. So there's no room for it to peek out, right? So let's continue with this. Let's try a higher value, 10,000 maybe. Yeah, it becomes a straight line, indeed. Now the opposite is true. As K decreases, we are going to see a stronger and stronger and stronger peak to the point that the rod is probably going to melt. Because the heat is not dissipating in the rod, it's just being concentrated at that one spot. So the temperature is going to keep rising and rising and rising and rising. Agreed? Because there's no room for the heat to go. So let's try it. Okay, so let's go to K equal 1. Okay, we started with 398. Let's go to K equal 10. Okay, indeed, the peak is higher now. Look at that. It's almost temperature, surface of the sun temperature, right? So almost 4,000 degrees, right? It's still, the boundaries are correct, but because K is so small and there's no mechanism for dissipation, the rod's probably melted. So at this point, this model is not valid anymore because you have phase transition now and the rod has melted and you're in a liquid phase, right? But at least the reasoning makes sense, right? And the pneumatics helped you think about that. If you drop K even further, you're going to get like wildly insane temperatures, which are unphysical, 35,000 degrees. You know, there's no material on Earth that sustains that temperature, right? Now, in reality, this model is a very crude approximation to what happens in reality. In reality, there's a mechanism on the heat generation that adjusts K based on the temperature. So the K value, that heat transfer coefficient, also changes with the temperature. So as you increase the temperature, K also increases, so you have more heat transfer because nature needs to find a way to just stabilize things, okay? But this is it. This is cool. I don't know, I get really excited when we solve this problem. And you can change the temperatures. You can do 400 on the left, 500 on the left, and 200 on the right. And let's come back to like a reasonable value here. All right, indeed, you get that same, all the trends. So you have thousands of variations that you can use and plug in and play around to manipulate this model. Do you have a question? Yeah.
This is like going back a little bit, but when we made the source, we had L over 3. Why, or like A equals L over 3. Where did the over 3 come from?
Yeah. So your colleague is asking in this A over here, okay? In this formula, A is the relative location on the rod of where the peak occurs. Okay? So when x equal a, what happens here? Think about this. When x is equal to a, you get e to the 0. So you get exactly 1 times alpha, so you get the peak. So the peak occurs at x equal a. So choosing a, you choose where you want the peak to be. All right, so how did I choose that? For this case, I want the peak to be at 2L over 3, or 1/3 from the right of the rod. If I want it to be in the middle, I'll go L over 2, right? Now, L is 1, clearly, but to be general, at L over 2, then the peak will be in the middle. See, right in the middle, and then this is what you get. Okay? So that choice of A is kind of arbitrary. It's like, where are you putting that flame? Right, on the 1/3 from the left, 1/3 from the right, or one right in the middle. Okay. Does that answer the question? Okay. Okay. Well, we're done with direct solvers. Next, we will start talking about iterative solvers. So it's good time to take a 4 or 5 minute break. Okay, let's resume. We're all done with direct solvers. numpy.linalgebra.solve or A inverse is your first go-to method to solve a system of equations, whether dense or sparse, tridiagonal. They're very robust. And as you saw with even a system of 1,000 equations, that's kind of very lightweight. It was able to do it very effectively and nicely. Don't fret about it. Now, you might end up doing some research with machine learning or data science. You have unimaginably large systems of equations to solve when you're doing regression for these multi-million parameters that you have to optimize for. So you need other types of solvers. Many of them will be available to you. And today I want to discuss about one specific class of solvers called iterative solvers, which is very, very specific for sparse systems of equations. Why do we choose sparse? Because they are ubiquitous. Like I said last time, all of these conservation laws, like heat transfer and thermodynamics, energy, mass, momentum, all of those result in systems that are sparse. You have first and second derivatives. When you numerically approximate those with derivatives, like we showed for this problem, you always get a few terms in the system of equations that are non-zero, and everything else is 0. So they are very ubiquitous, very important use cases. And we defined sparsity last time as being the ratio of the number of 0 elements to the total number of elements in a matrix. And we said a matrix is sparse if 50% of those elements are 0, if the sparsity is 0.5. If the sparsity is 0.5 or 50% of the elements are 0 in the matrix. Okay? All right. Now, iterative solvers are designed to specifically target sparse systems. Why? Because we observed as we use direct solvers and we go to 2 dimensions, 3-dimensional problems, like if I'm studying the airflow in this room and how there's heat exchange between the inside and the outside, this is a 3-dimensional problem. The cost of solving is unimaginable. And the space storage requirements are very complicated. Again, I've showed a few diagrams on that. Hence, the idea of iterative solvers came about. And someone, starting with Jacobi, said, well, you know what? Let's not solve this exactly. How about we just get an approximation to the solution? How about we start with a guess and then refine the guess to get to a better solution. Okay, and then the other guy said, okay, how do you refine the guess, Jacobi? He said, well, I have the system of equations. I have the governing equations of this set that I'm trying to solve. So why not use those to refine the guess? And was born the first idea of iterative solvers. Again, I mentioned this last time. The critical issue, though, for iterative solvers is that they have to operate on a system of equations that is diagonally dominant. What that means is when you write the system of equations in matrix form, and you go row by row, remember each row represents an equation, the entry on the diagonal, the coefficient of the diagonal item needs to be larger in absolute value than the sum of all the off-diagonal components in absolute value. So in other words, this math formula, for a given row in the matrix, the diagonal entry in absolute value needs to be greater or equal to the sum of the absolute value of the off-diagonal components. Otherwise, you will not converge, or you will see very, very weak convergence. I was testing a few cases before coming to class where the diagonal entry was exactly equal to the sum of the off-diagonal entries, and the convergence was very, very slow. Fortunately, the systems that we encounter in engineering are indeed very strongly diagonally dominant in all these conservation laws. So we're good to go. They're great use cases. Now, oftentimes, if you don't have diagonal dominance, you could rearrange the equations such that you get diagonal dominance. And this is called pivoting. There are two types of pivoting, row and column pivoting. And again, when you think about matrix, think about a system of equations. When you pivot a row, it means you're rearranging the order of the equations. When you pivot a column, you're rearranging the order of the variables, because the columns represent the variables. All right, so take this system, for example. If you look at the main diagonal of the first row, the main entry is 0, and it's not greater than 1 plus 3. It's actually less than 1 plus 3. So that alone will kill an iterative method for this system. However, as you go down, the second row, 2, the main diagonal entry is 2. It is greater than 1 plus 0, which is great. But then you go to the last one. Again, the main diagonal entry is 2, and it's less than 4 plus 1. That's the condition for diagonal dominance. So what you can do here, if you notice the first and third equations, if you swap them, you get diagonal dominance. And you still have the same system of equations. So if you take these two and just simply swap them, get the third equation, put it first, and the first equation, put it last, and just simply adjust the right-hand sides, then you get diagonal dominance. 4 is greater than 1 plus 2. 2 is greater than 1 plus 0. 3 is greater than 1 plus 0. Okay, that's row pivoting. You rearrange the equations. You didn't do anything. You just rearrange the equations in the matrix. Because when you're given a system of equations, you can put any equation at the beginning, any other equation at the end. Doesn't matter. Okay? The ordering is completely arbitrary. Same way with the variables. The way we choose to order our variables is also arbitrary. Right? For the temperature problem, we could have chosen to start with the middle temperature and then go alternating directions, right? It would mess up the matrix. We look very weird, but it will still be a valid system of equations. It will be the same system of equations. So with column pivoting, you rearrange the variables. So if we take these two columns and swap them, now these two columns are associated with those variables, right? So that first column is always multiplying x1, and the last column is always multiplying x3, right? And when you take the matrix vector multiplication. So if you swap these columns, you also have to swap the variables, right? Just to stay consistent in the system of equations. And again, you get diagonal dominance. 3 is greater than 1 plus 0. 2 is greater than 1 plus 0. 4 is greater than 2 plus 1. Okay? Very simple trick. It's always done. All right. Now we get to the first solver. The Jacobi iterative solver is the simplest iterative solution. It belongs to a class of academic type iterative solvers. We rarely use those in real practice. In real practice, we get to these like high order Krylov multi-grid spaces, which are like beyond beyond imaginably complex. There are people who dedicate their lives to study these, to develop these solvers. But yet, it doesn't mean we cannot understand how they operate in their essence. And the idea of the Jacobi iterative solver, like I said, is, just like you take a single equation, ax equal b, and you can simply say x equal b over a, right? So you can simply draw x out of it. What if, Jacobi said, what if for a system of equations, and I'm using this nomenclature again, A11, A12, A21, A22, so think of this as a matrix. I'm calling this equation 1 and this equation 2. And he said, okay, bear with me, this is really cool. What if we solve equation 1 for x1? So just put x1 on the left-hand side, move everything to the right-hand side. Before you tell me what's happening to x2, okay? Before you say that. And solve equation 2 for x2. Okay? That's still the same system. We haven't done anything, but what's the point, right? We still don't know what x2 and x1 are, because x1 is that equation and x2 is this equation. It's like gets really tautological and circular. But this is where numerical methods comes in. What if we put guess values for x1 and x2? Remember, I said if we start with a guess value for the solution of the system and somehow refine that guess, could we get to a solution? How do we refine the guess? We use the system of equations that governs those variables. This is it. That's using the system of equations, these equations that contain x1 and x2, but then choosing to start with an initial guess on the right where the blue is, and saying, okay, I'm starting with some guess for x1 and x2, and I'm going to improve that guess by applying this recipe. So we call that initial guess, we give it an index 0. So x1, 0, x2, 0. There's not a power, it's a counter. Okay, that's the initial guess. So start with any value, 0, 0, 5, 3. Plug it in, and compute a new value for x1 and x2. So when you think about it this way, what this operation is doing is taking an initial value for x2 and x1, initial guess, changing it a little bit, and making a better guess for x1 and x2. Now what do? You take that. Let's call it x1, 1 and x2, 1. So that's the first improvement, right? So the first improvement, 1, that counter, watch that counter, is based on this initial improvement. Now we have 2 new improved values. You can plug them back in the system of equations and check. Are they the solution? Probably not. So what do? You take them and repeat. Then you take the x1 values, put them in that same formula from the system of equations, and improve them to get second iteration values. This process is called iteration. You start with a guess, and you keep improving that guess using the system of equations until you hopefully converge. And guess what? It does converge. There's all sorts of math theorems telling you that if the system of equations is diagonally dominant, this method will converge to the true solution. Again, use x1 and x2 for the second iteration, and apply that same formula. It's the same formula over and over and over again, but you keep changing x1 and x2 all the way ad infinitum, all the way to however many iterations you like. So in general, we write this procedure as x1 at k plus 1. The k plus 1 value of the iteration is this formula based on the kth value. The kth value are the past. The k plus 1 value are the improved, the future. Same thing for x2, right? And x2, the improvement for x2 is based on the equation of x2. The improvement of x1 is based on the equation of x1. It's just rearranged in a way that we can extract the answer very quickly. It's crazy that such a simple idea, like This is not exact math. I'm not saying x1 equal x1. See that counter? I put x2k plus 1 and then x1k. Those are two different values. Okay? So this x1k is not x1k plus 1. Those are two entirely different values. Now this process is called an iterative process. That's why we call them iterative solvers. You start with a guess, you apply a recipe to it to improve it, and you keep applying that recipe over and over again until you get to an answer. Here's an example. And you should do this by hand. It's a very simple example. I'll give you the first iteration and a table, and then you can do it by hand, do a couple of iterations just to kind of see how the process works. If we start with an initial guess, x1 and x2 are both 0, then the first iteration, as from the previous formula, is 1 over a11, right, which is 1 over 4, times b1 minus 3 times x1k, right? So it gives you 2.5. Oh, look, we started with x1 equals 0. Now the new value of x1 is 2.5. For x2, we started with a value of 0. The new value of x2 is 2.8. So it changed. Now you take 2.5 and 2.8, treat those as your new initial guesses, and you repeat. And you repeat until you can no longer improve. So if you do this over and over and over again, if you're counting the number of iterations, this k equals 0, so that's the first iterate, second iterate, and so on. After k equal 100, you get to the exact answer almost. Okay? You just keep repeating and repeating and repeating. And see how it converges. It fluctuates. It went from 0 to 2.5, 0.4, 0.7, 0.46, 0.5, 0.4, 0.1. It's kind of stabilizing. It's like trying to find the right answer. And it works. It magically works. And that's the idea of iterative methods. All iterative methods are based on this. OK, so now this is for a 2x2 system. Let's generalize it. For a general system, n by n equations and n unknowns, we write it like this, familiar with that notation. And I'm writing the diagonal entries in red. Why? Because, again, the idea is solve equation 1 for x1, or equation 1 for the first variable, equation 2 for the second variable, equation 3 for the third variable, and so on. You just simply extract that variable out and take everything to the right-hand side, divide by the coefficient, and extract that value. If you do this process, then you get a general formula for any variable. So the I is the index of the variable. So this could be the first unknown, the second unknown, the third unknown. You put I in here, right? The k plus 1 iterate for xi is equal to this really neat, simple formula, 1 over aii, which is the diagonal entries, right, times bi, which is the right-hand side. Again, think of I as x1 or x2 or x3 or xn, right? So we're going to do this in one shot, all in one shot. We're going to loop over each row, as you'll see, each equation, and so find the updated values. Now, this summation over here almost looks like a matrix vector multiplication. If you remember when we wrote things in matrix form, I had this kind of summation of aij times xk. When you see this, if you saw this, this is nothing more than matrix A multiplied by this old solution vector. However, I have this condition here that I is not equal to j. Okay? Why is this the case? Because if you notice, for equation 1, we're solving for x1, so we took out that aii or the xi case, right? So if I is equal to j, that means that we are on a diagonal entry. No, the diagonal entry, we moved everything to the left-hand side. We're solving for those, right? So you just have this little condition. Otherwise, this was to have been a really neat matrix vector multiplication to do. But it doesn't work that way. Now, when you program this, we will be doing a for loop. And I told you in for loops, I really hate if statements. Because for a for loop for this summation, to prevent adding I equal j, you're going to have to put, if I is not equal to j, then do this. Otherwise, don't do anything. And I hate if statements. So there's a little trick that you can do to get rid of this I equal j, I simply add and subtract that missing term. So if I add and subtract aii xi k, the kth iterate, if I add it and subtract it in those parentheses, I'll take one of it and put it in the summation. So then we will have the full summation. And then you'll end up with one extra term over here, because this was aii xi to the k, and divided by aii, you get xi, not to the power, the kth iterate. And then this looks more programmatically simpler because I don't have an if statement over here anymore. This is simply the entire matrix multiplied by the old values or the previous values of the iteration process. The way I think about this, and sorry, I'll have to adjust the parentheses here. These are not powers, okay? These are parentheses. They are a counter. The way I think about this is the improved iteration value is equal to the old iteration value plus a correction. That's how I think about it. When something like this might look ominous because aij and whatever, it couldn't be easier. Once we get to the programming, you'll see it's just a matter of multiplying things together. Okay? The algorithm is fairly simple. You start with a guess, and then you implement this formula. And you keep iterating until you reach convergence. Okay? We're going to spend some time talking about convergence. But let's go ahead and program this together. I will also give you the code for the Jacobi iteration in the homework assignment, and I'll put it on Canvas. So you're welcome to use whatever we develop in class or whatever, or the file I give you, or write your own. All right, so, but we'll program it together just for the sake of, opportunity to see how we could program something like this. All right, so if we were to apply this for another system, here's another example, by hand and computation. The exact solution for this other system is 0.9 and 3 and 2.3. You eventually get to the right answer, okay, after a lot of iterations. But eventually, the convergence starts slowing down, okay? So keep that in mind, because we're going to touch on this a little later, all right? So let's get our notebooks now and see if we can program a Jacobi iterative solver and use it to solve this system of equations, okay? We'll do it together. So I'm going to create a new notebook here. Okay, I'm going to iterative solvers in class. Okay. So again, I would like to import the boilerplate. Okay. That's my boilerplate. And let's grab the formula for Jacobi. So I will move it over here. And look, you can ask GPT to give you a Jacobi solver. But then when I ask you to start changing the norm or just changing the maximum number of iterations, if you can understand how to fix it, that's great. But if you don't, you're creating more trouble for yourself. So be careful, right? If it helps you learn, because GPT can produce a code for Jacobi, but it might not be the code that is adjustable to the way I want you to adjust it, or you may want to adjust it. But if you can understand what GPT is giving you, that's great, because it's a learning opportunity, and then you can make it even better. Okay, so let's see. All right. So for Jacobi, I would like to start defining a routine. We'll call it Jacobi. Very simple. All right. What inputs do we need for this Jacobi solver? So let's look at the formula again. This was the formula, x to the, I can't even see from here. The k plus 1 iterate is equal to the kth iterate plus a bunch of things here. And the algorithm said that we need an initial guess, okay, and to compute those. All right, so what do we need for this? What do you think a routine for Jacobi is going to require? What inputs? Okay, initial guess. Let's just do it one by one. Okay, so we need the initial guess. Let's call it x guess. Okay, what else? What are we solving? What are we solving? General relativity equations, or like what are we solving? A system of linear equations. So what do we need from that system of equations? The x is the solution, right? What about the coefficients? Right? So wouldn't that be an input for Jacobi? Right? Look, guys, here. This, to evaluate this formula, we already brought in the guess. So we're starting with an initial guess, okay, for k equals 0. We know the guess. We still need the bi's and the aij's, right? So we need the coefficient matrix. That's essential. That's a no-brainer, right? All right, so let's do this. We start with the A matrix, coefficient matrix, and the right-hand side, and an x guess. Do we need anything more? Well, not right now. At least not right now. Okay? All right, now I'm assuming that the array, you can do all sorts of error checking, etc. We're going to circumvent that for a minute, but I'm assuming that A is a NumPy array. Okay? Assuming that A is a NumPy array. Now, to do this loop, I need to figure out the size of this system. So the number of equations. And again, I'm assuming that this is a correct system of equations. So it's an n by n matrix. So the coefficient matrix that the user is bringing in is correct. It's not some m by n or like 4 by 6, right? It's invertible. So you can add error checks to say, well, your matrix is not a square matrix, so I'm not going to even attempt to solve it. So we're going to assume that all of those are the case. And we can simply get the number of rows or the number of columns and say that, this is len of b, right? The length of b gives us the number of rows and also the number of columns. Why do I need n? Because of this summation, right? I need to sum up over all of those values. And I need to go the variables, the solution, I need to go from variable 1 all the way to variable n. So I need a for loop. There's no way around the for loop. Okay, there's no way to vectorize this in a clean way. Okay? All right, so I will also need a counter, my iteration counter. Call it iter equals 0. That's like a iteration counter. Iteration counter. Right, because we need to repeat this. That's k. That's our k in the formula. All right? I will also need to initialize the solution vector. I'll initialize it to 0. np.zeros will n. Now, just like NumPy provides an array of 1s, it also provides an array of zeros. There's no better initial guess for my solution, or not guess. There's no better initialization for my solution variable than for it to contain just a bunch of zeros. Okay. All right, so how many iterations are we going to do? 1, 5, 1,000? Okay, how about we provide that as an input by the user? Okay, so let's do max iter as an input. Max iter as an input by the user. Then here we can do a while loop. While iter is less than max iteration, do something, and then increment iter. Okay, so do a bunch of things, and then increment my iteration counter. Okay, so that at least gets me in this loop to start with k equals 0, k equal 1, k equal 2, and so on and so forth, right? So iter is iteration counter. That's like k in the formula for Jacobi. Okay. Okay. So now I need to go over each variable. There's this I here, the subscript. I need to solve for unknown 1, unknown 2, unknown 3, all the way to unknown n. And I'm going to go through those one by one and implement the formula for each one. Now think of this as I'm going over the rows or the columns. I like to think of it as I'm going over the rows. Okay, so I'm going to loop over row 1, row 2, row 3, and so on. Okay, so let's do that. That's another for loop. Okay, let's say loop over the rows slash unknowns. Okay. For I in range from 0 to n, right? Now remember the range function. It just gives you a sequence of numbers starting from a value and ending in another value minus 1. Now why did I start from 0? Because everything is indexed at 0 instead of 1. So truly my first entry in the diagonal is A00, not A11, okay? Unlike the math that we put in, so that's just a little inconsistency between the math and the programming. So I have to start from I equals 0. And then simply, what I have to say is my solution at I, so the variable I, the ith variable, the new value is equal to the old value, which is x guess at I, plus 1.0 over AII. So for a two-dimensional NumPy array, remember this is how you index an entry in the array. Like A, it's just like AII. You're just trying to be faithful to the formula over here. So that's 1 over AII times B at I minus, okay, now remember why I added this xik to convert this into a simple matrix vector multiplication. So I don't have to do another for loop with an if statement. So this sum aij xj is nothing more than the dot, than the matrix vector product. And remember the symbol we used last time, the at symbol? That's what we're going to use here. Minus a I at x guess. Now x guess contains the value at the kth iteration, right? So the old values. And AI is going to give me the row that I'm interested in, right? It's going to give me that one row. For equation 1, I'm solving for equation I, think of it this way. For equation I, I'm solving for variable I, and it's equal to the old value of the variable I, of the ith variable, plus 1 over the diagonal entry at I, right-hand side of variable I, and then the row, that entire row of that ith equation, okay, all the coefficients, times all the guesses, right? Because we're bringing in values from x1, x2, x3, x4, etc., all of them together. Okay, now this is not enough. Because once we're done with this for loop, I need now to make my new values the new guesses, right? So that's a simple thing. I reinitialize my x guess, and I make it equal to, I make a copy of my solution. Okay, so this used to be a homework assignment 5 years ago. Now I'm like doing it in class, and I'll give you the answer. So, don't worry about if this is, too much or not. But you'll have the access to the code, and at least think of it as an opportunity to maybe, this is how we think about coding something that's a little more complex. Okay, and you're welcome to come back to the lecture, video, etc. Maybe later you're implementing something like it, and you wanna remember how we went about this. Okay, but this will be given to you. Like if this went over your head, that's okay. Don't feel bad about it or guilty. Okay, I'm not holding you responsible for this. And then we return the solution, return solve. Okay. All right, so let's see if this works. So the system we're trying to solve is this one, 511-230-304, with the right-hand side 10, 11, 12, and with initial guess 111. Okay, so let's implement this. This is a small matrix, so I'll build it as a simple nested lists with an NumPy array. So I'll open the first row is 511, and I should put point zeros everywhere. Okay, and then 2, 3, 0 for the second row, and the third row 304, 304. Okay, right. So that's my coefficient matrix. My B is in another NumPy array, and that is really simple, 10, 11, 12, right? 10, 11, 12. And my X guess, or X0, let's call it, is another NumPy array, numpy.array, and we'll start at 1, 1, 1. All right, so let's try it, Jacobi. And what do we need to pass? The coefficient matrix A, B, X0, and let's say 10 iterations. Oh, look at that. It returned a solution. After 10 iterations, okay, look at this. This is what I got here from the answer, right? It did return a solution. Okay, how about we dig a little deeper into it and maybe do some printouts inside the, inside here. So let's say we want to see how the values are evolving per iteration. So print, I want to print the value of the iteration I, and then separated by a tab, the value of x1, the value of x2, and the value of x3. Okay, /n. And then we'll make it a little nicer, print some horizontal lines over here. And then we can go ahead and print the x values. Let me see, print, enter, okay, print, iteration, and then another tab, and then all the solution values. Let's see if this works. Oh, perfect. Okay. So, starting with an initial guess. Oh, wait a minute. Doesn't make sense. 0. Oh, yeah. So the solution initially is 0, 0, 0, or could be initialized to the initial guess. And this is how the variables are evolving. The first variable, x1, is going 1.6, 0.95, 1.12, et cetera, and then finally stabilizing. Same thing with the second variable, 3, 2.6, 3.0, 2.9. It's like they oscillate initially, and then they stabilize to a fixed value. Okay? And that is going to be a common theme for all of these iterative solvers. Okay, but what if 10 iterations is not enough? Remember the Taylor series? Should you put 1,000 terms or 5 terms? Right? What if that's not enough? What if it's more than enough? You can put 2,000 iterations, and you might get the answer in 5 iterations or 10 iterations like here. So what's the point? Right? So we need a better mechanism to evaluate how well our iteration is converging. And guess what? What kind of error is perfect when we don't know the answer, the true answer? Is an approximate error, right? So if you think about this, notice here, after some point, we no longer improve on the first 3 significant figures, right? We start the third one, and then so on and so forth, right? So you can say, well, when you stop improving on the third significant figure or the fourth significant figure, that's a relative tolerance, right? That's a relative error of 2% or 1% or 0.1%, right? Then stop. So that's exactly what we need to do next. However, we have an issue here because we don't have a single value. With the Taylor series, we were evaluating sine x. That was a single value. Here we have 3 values. In general, you have 1,000 values. Okay, so I have to go back to the slides to make this a little clearer. Okay. So when do we stop iterating? If you look at the approximate relative error between the iterations, that could be a great indicator, right? You see after a while, the iterations, they stop improving on the value. So you could just stop right there. But there's a problem here. You can define an error for each variable, right? A relative error or an approximate relative error or an approximate error, relative or non-relative, doesn't matter. But you can choose one error and define an error for each variable. You can see for variable x1, our approximate error started at 10 to the minus 1, then it hit 10 to the minus 7. But then the relative error for the second variable, so these columns, they contain just the difference between successive iterations, right? Then this one is 10 to the minus 7, this one is 10 to the minus 9, and this one is 10 to the minus 9. So one of them is larger than the others, one of them is smaller. So which one do you choose? Which one do you choose to determine whether you're converging or not? Do you choose the worst one, the one that's converging very, very slowly? But imagine you only have one variable that's converging very slowly, but all the other ones are already at 10 to the minus 11. Doesn't make sense to keep iterating just for that single one variable, despite its importance. Okay? So which one do you determine? Well, let's look at it a different way. Together, the errors for a given iteration, you can compute an approximate error for each variable. Okay? Now, together, those errors, they make a vector. Okay? How do you evaluate the magnitude of a vector? Remember exam 0? Right? Pythagorean norm, for example. Right? Some measure to tell you how big that vector is. Like, what is the magnitude of that vector? Right? So we need some collective, or you could say we'll take the average. That's also a measure of the size of those errors. Okay, what's the average error? If variable 1 is committing an error 10 to the minus 7, variable 2 an error 10 to the minus 9, we take the average and we say that's going to be, we're going to hold the system accountable for that error. That's completely legit. Okay, but you have to choose one. Okay? Now, because if you think of those as a vector, that opens up an entire world of possibilities with what we call vector norms. So the Pythagorean norm that you're all familiar with, which is the square root of a squared plus b squared, or the square root of a squared plus b squared plus c squared, etc., that's called a norm. It is a measure of the size of a vector, but it's not the only way we can measure the size or the magnitude of a vector. What I'm presenting here are 3 norms, and they are given in this double, these two vertical bars. It's not an absolute value, it's a norm. Whenever you see in this class those 2 vertical bars, it means I'm trying to measure the length of something. You can define the first norm, designated by this subscript 1, that first equation, and it's simply the summation of all the entries in the vector in absolute value. So you're just simply adding a plus b plus c plus d in absolute value. The second norm, a2, that's your Pythagorean norm, the square root of the squares of each one of those, sum of the squares, right? So square root of a1 squared plus a2 squared plus a3 squared, etc. Right? That's just your standard Pythagorean norm. Finally, there's the infinity norm, and it says, you know what? Take the maximum, the worst offending, the maximum value in that vector. So when you think about this in the errors, that would be holding the system accountable to the variable that is converging the slowest. Okay? These norms are called L norms, right? For some reason, some vector spaces. So L1 norm is just simply the summation of all the entries in the vector. The L2 is the Pythagorean standard norm, and the L infinity is the worst case scenario. And you can get those very simply with Python. You don't have to compute them one by one. You just call numpy.linalgebra.norm. You give it your vector, or the error array in this case, and you choose one of the norms, 1, 2, or infinity. And it doesn't matter which one you choose, as long as you are clear about it. I personally really like the L2 norm, or the Pythagorean norm. And then you can simply compute the norm of the error at each iteration and then stop when that error is below a certain tolerance. Right? So you're no longer measuring the error for a single value anymore. You're measuring the error for a collection of values. Each value has its own error. You need to aggregate all those errors together. You can take the average, you can take their sum, You can take the square root of their square of the sums, sum of the squares, right? They're all reasonable. They will all be close to each other within a few iterations, but you have to choose one of those as you're designing your solver. So for this problem that I showed, this is what this would look like. Now each row here, so the columns, they represent the errors. So the error, the approximate error for variable 1, variable 2, variable 3. And then the last column is the sum, is the square root of the sum of the squares of these. And it gives you an aggregate value of the error. Like if you look at this row here, you have 10 to the minus 7, 10 to the minus 9, 10 to the minus 9. The aggregate value is dominated by 10 to the minus 7. If your tolerance is 10 to the minus 8, you'll continue iterating. Okay?